welcome back to this NPTEL online course on molecular rearrangement and the reactive intermediates. In the couple of classes, I am trying to solve several problems from the different chapter which I have covered in the class. I already covered problems from the carbocation, from the carbanion, the carbene. Also, you have seen the problems from the sulfur and the silicon. In the today's class, I am going to show you some problems from the organoboron chemistry. So let's start with the first problem. So in the first problem, we are going to talk about the hydroboration reaction here. So here we have this this olefin here, and you have 9 BBN, and you are using a H2 to NaOH. So we have learned about this important reaction called hydroboration. So hydroboration, there is two important facts you should remember. One is that boron hydrogen approach in the same phase of the olefin. So if you have olefin here, both come from the same side of the olefin. Okay, so that is syn addition happen. And then the second thing is they follow the anti-Markovnikov rule. So let's go back to that rule which I'm going to talk about. What does that mean here? That means we have learned that according to the Markovnikov rule, if you have a olefin, like, let me just write down an example here. If you have olefin like that, and if you adding a boron here, like 9 BBN, let's think 9 BBN, and what is going to happen? You end up forming the boron here. So you can write 9 BBN and H. So that means what is happening here? The boron is going to the I think if you forgot the structure of 9 BBN, let me just tell you one more time the structure. It is why I am drawing this, because so this is the structure in synthesized from the corresponding cyclooctadiene. So from cyclooctadiene, if you treat with BH3, it is going to convert you to the 9 BBN. So sometimes people write 9 BBN H also. So then what is going to happen? This can go for a hydroboration with olefin, and the boron comes in the terminal carbon. So that's why this is that's why we called it as a anti-Markovnikov rule followed. So now you have to understand why that is happening. So one of the reason is the steric. So one of the reason is the steric factor. Okay, and then also we also consider that when the boron and hydrogen is coming, we always write this as a like a delta plus and a delta minus. Okay, now if it is a delta minus, the hydrogen, because you can see according to the electronegativity difference, the hydrogen will have a more electronegative density. Hydrogen is more electronegative than boron, so hydrogen have more electron density. So it is going to add to that corresponding carbocation, because now this delta minus will try to add a delta plus, more delta plus. So that means if you think about these two carbon, and if you try to think about a delta plus in these two carbon, when it is going to form the carbocation, then this is going to form. So in terms of carbocation formation, you can think that this is a secondary carbocation if it is forming here, versus a primary carbocation if it is forming here. So of course the secondary will be more stable compared to the primary. That means if you see out of these two carbon, this carbon will form more carbocation. That's why the H minus, this H of the boron which attaches to the boron will add onto that particular carbon. That's why the hydrogen comes in the internal, the boron comes in the outer carbon. Okay, so that, and also there is a steric factor. So now if you see in this example, we can clearly see that similar things, that if you think about this particular carbon and try to think about in the manner of a carbocation, this will be a tertiary, this will be a secondary. That means your hydrogen going to add here. So if you are trying to draw this particular compound, what we are going to see that this is a trans so yeah, this is a trans decalin system. And you have a double bond and a methyl here. So now what is going to happen? If you are so there will be a syn approach of the boron and hydrogen, and you have you seen the hydrogen and boron going to be in the same side. So now if you treat with the 9 BBN, it is going to add from the same site, and that means if it is adding from the same site, it is going to generate a product. Either you can think about that this will be like this one, so you will have a boron here, because if the hydrogen come from the bottom phase, then this will be okay, then this is the boron, okay, and then, or it could be have another one, you can draw here, where so there is a possibility of both of these. Let me try to find out which one will be, and then your H is here and your boron is here. Okay, so this is from the top phase versus from the bottom phase. So now if you try to understand that, we have to draw the corresponding conformations. Okay, so if you try to draw that, then we can clearly see so if you draw them as a trans, and we can find out that there is a olefin in this particular carbon. Okay, so if there is a olefin here with a methyl group on the same plane, then you can, so you have a hydrogen here and hydrogen here. That means now they can approach from either from this side or from this side. Okay, so if it is approaching from this side, you will be able to get this one or this one. Now either of this compound, once you treat with the corresponding H2 to NOH, you know that it is going to convert to the corresponding alcohol. So you end up getting the boron will be replaced to corresponding OH. Okay, so now if you look into the corresponding the option which is given in the exam, so you can see that both, one of the important thing is the methyl and OH will be trans. So let's look into the option where, and then this is a trans decalin, so you have to see that this relationship is maintained. So all the product has trans, but in this case the OH and the the OH is in the above phase, the methyl is in the down phase. In the next option, both methyl and OH in the same phase, so that cannot be the option. Both methyl and the OH in the same carbon, that cannot be the option. And also both methyl and the OH in the same site, that is not the option. So the option A is the only correct option. Okay, if you again forgot the hydroboration, please go back to the respective node of the hydroboration, which I already covered in the organoboron part. You can get more idea about it. Again, I talk about some of the the reducing agent using there are several boron based reducing agent I talk about. So now we can talk about here, I think, using a boron, and I mentioned that if you have a carboxylic acid, the boron will selectively reduce the carboxylic acid in presence of the ester. And if you remember, I already talked about the mechanism, how that happens, that if you have a carboxylic acid and if you have a boron or BH3 or B2H6, then the boron bind here. So boron coordinate with it, and then what is going to happen, this can H minus can take this proton and this bond can form. So this way you will be end up forming and there will be BH2, and this can again this can react with another 2 equivalent and form this one. Okay, now what is can happen, now this can treat with another BH3. So this now it can attack to the corresponding oxygen, and now you will be finding out that there will be a H going to come here, the oxygen is going to bind with a boron, and then here there is a boron also. So you'll be able to get some sort of species like this. From there you can clearly see this is going to get hydrolyzed and gets to corresponding aldehyde, because one of the, so this is this is going to convert to some oxygen will be still at some boron will be still attached, and this is the boron, and there will be a H here. Okay, so this species eventually what is going to happen, this is going to get reduced again by BH3, because the boron is activating this carbonyl, some sort of a delta plus, so BH3 going to reduce it to all the way to the corresponding alcohol. Okay, so it is going to convert this, so it is going to go for another batch of reduction to get all the way to the corresponding alcohol. So what is going to happen in these cases also, you will selectively going to reduce them to the corresponding the ester will be remain unreacted, you will be forming the corresponding alcohol. Now once the alcohol is formed, you have a ester, this can form a lactone. Okay, because at the end you will be having this O minus and the boron will be attached, so that can all the way participate, and then you have given the H plus also, so this will take you all the way to the corresponding there will be CH2 here, there is a methyl here, going to come back to the stereochemistry here, and then there will be CO. Let me see if I am missing, oh there is one carbon missed, so this will be CH2OH, sorry, because you have a CH2 here, and then so it will be CH2 CH2OH that will end up forming this compound. Okay, now let's think about what will be the stereochemistry here, because you have to understand once this is getting cyclized, your stereochemistry will be written here. So that means if this stereochemistry was R, it will be R, or if it is S, it will be S. Okay, so let's try to think about the, if I try to go for the priority, this will be 1, this is 2, and this is 3. So this is 1 2 2 2 3. Okay, so this is supposed to be clockwise, but your 4 is actually above, so this is going to be S. Now if you come here to make it S, you can think about, so this is your number 1 priority group here, this is your number 2, this is number 3. So if you go from 1 to 2 to 3, this is anti-clockwise, correct? So to make anti-clockwise, the 3 if is above and 4 if is below, then this is going to be S as well. Okay, so the correct answer will be where you will see both methyl and you can see, so let's look for all the different answer here. Then this cannot be the correct answer here, because you have changed the stereochemistry of this center, that should be written. So only B and C has the perfect stereochemistry for this center and this center, but only in case of this one, you can see it is matching with our product, but here they have done the reduction on the ester side, but it is going to only the reduction going to happen on the acid, not on the ester. So that cannot be the option, as well as this is cannot be the option as well, because this is also doing the reduction on the ester, not in the acid. Okay, so the option B is the correct option. So let's go to the next problem. So here we can see this is a reduction of a enone. In this problem we can see there is a reduction of enone to the corresponding, you can see a allylic alcohol, from enone to allylic alcohol. Now in this reaction they have given the condition like H2 palladium carbon. Again, if you use that, you can only reduce the corresponding double bond, not the carbonyl. If you use the Wolff-Kishner condition, it will only going to reduce the corresponding carbonyl, not the olefin. And then that can give you a product where your carbonyl is gone but your double bond is remained. That is not the product. So if you want to reduce the carbonyl group, then you have to use the Luce reduction, which we have discussed, using sodium borohydride and the cerium chloride. So here what is the what is the problem if you use only sodium borohydride? If you use only sodium borohydride, the problem is sodium borohydride will go for both 1,2 addition, 1,2, where it will form this compound. Sorry, this will be where it will go for the desired compound, plus it will go for some amount of 1,4. So in that case, what is going to happen? You will be so you will be adding. So you will first actually you go for 1,4 addition, and then you reduce the corresponding carbonyl group, so that will give you all the way to this alcohol, which is not having this double bond here, and you will get the get as a mixture of these two compounds, and there is not much selectivity. You will get like something like 60-40, 70-30, depending on the substrates. So to avoid that, it was developed that if you use this cerium chloride with methanol as a solvent, which is the key for this reaction, then it will form some sort of a tangent state like that, where the methanol hydrogen is going to, so the cerium 3 going to form a Lewis acid base adduct with the oxygen, that will generate a delta positive charge, and this H going to bind with the carbonyl oxygen. So that way now this center become really hard because of the electron withdrawing from the oxygen. So now the sodium borohydride, the H minus, so this H minus is going to selectively act to the carbonyl group. So you will end up only forming the desired product, which is the allylic alcohol. Okay. Let's see the next problem. So here the first thing is they are asking that if you have a cyclopentadiene, if you use BH3, what will be the product? And now if you treat with these particular compounds, what will be your product? And then so there is 3 different transformation, and then at the end they are giving you this vinyl iodide with palladium catalyst and cesium carbonate, DMF water. What will be product B? So let's find out what is the product A. Okay, we have already learned that if you have a the cyclooctadiene, and you treat with BH3. So first thing is will be hydroboration. Of course, the BH3 will be with SMA2 or diethyl ether. So it will going to form the corresponding BH2, and then it will go for another internal hydroboration to form BH. Okay, so that will be your compound A. Okay, so now what is the next thing? Once you have that, you treat with this particular compound. So you can see in this compound you have 2 different olefin. One is a disubstituted one is a terminal one. As the 9-BBN is a bulky hydroborating agent, I think I talk about those things, that why we are not using BH3 all the time. If you use BH3 all the time, you will not be able to get a selectivity. Means the hydroboration can happen if you have a if you have some sort of a bulkier or more substituted versus less substituted, or you will not be able to do a much differentiation in the hydroboration. To make the differentiation, this type of bulkier hydroborating agent was developed. You can get a list. There are, I think I talk about the Cial boron, and also the pinene boron. So you have seen those things, and I have already covered their the reactivity in the class. So here, because of this reason, that it will going to prefer to add with the terminal one instead of the internal one, because of the steric. So that's why you will be only forming the hydroboration. And again, if you remember the hydroboration here, the boron will be in the, follow the anti-Markovnikov's rule. So the boron will be in the terminal position. So you will have a 9-BBN here, and H will be adding in this carbon. And once you have this compound, now you are treating with corresponding vinyl iodide with a palladium catalyst and a base and DMA border. I think you can remember this reaction which I covered in the class, correct? So this is a Sujui coupling with alkyl boron reagent. So not that the Sujui coupling always happen with aryl boronic ester or the aryl boron compound. It can also happen with alkyl boron compounds, and I have already discussed this reaction in the class. That means once you have a alkyl 9-ppn compound, of course you have to use some of this arsenic, the pH3 as a ligand. This is a very superior ligand which can stop the beta hydride elimination. So that can allow the corresponding Sujui coupling to take place. So what will happen? This iodo will be, so this is go for oxidative addition, and then there will be a the transmetallation. So if you remember the mechanism, I think first oxidative addition, then there will be, after them there will be I'm just not going to write all the different steps here, but the boron will be eventually going for transmetallation, and okay, so you will be forming this one, and then from there will be reactive elimination, and that will take you to all the way to the product. And the important thing to note that if you start with a vinyl iodide which is so you can see this is Z olefin or cis, both these groups, then in the product also that will be, and that is going to be retained. So you will have 2 carbon here, and then so now if you look into all the different option given, let's look into all the options. So this is the structure of the 9-ppn, so these 2 seems correct. Now look into the option B. In the option B we can clearly see these cases they are showing the product which we got, and this is the geometry which is written, but here they wrote a trans, so that cannot be the correct answer. So the option A is going to be the correct option here. Okay, so there is a hydroboration first to generate the reagent, then another hydroboration, then there is Sujui coupling. Write down the major product in the following reaction. So this is a very interesting question here. We are talking about the hydroboration for alkyne. So very similar to the olefin, the hydroboration can also happen in the alkyne. Now the question comes, if you see in this particular system, this is not a symmetrical alkyne. I think I already talked about this type of problem in the class. This is an unsymmetrical one, and again you can see they have a different in the electronics. One is electron rich, another is electron deficient. So now if the bromine is electron withdrawing group, then it can able to generate more delta positive in this particular carbon compared to the other one. So that means now if the boron is going to add, H is going to prefer to add in this carbon compared to the other side. Okay, so this way the hydroboration going to take place, and you are using a cyclo, a boron which is having a H and a cyclohexyl. So this is going to add here, and once the hydroboration going to take place, will be end up forming this compound where the bromine and the corresponding N-butyl will be in the same site, and the H and the cyclohexyl boron will be in the same site. Okay, so now what is happening? You are treating with CD3 or I think I already talked about in this class that once you treat them with the acid, then this bond is labile, which will be replaced by the acid hydrogen. Okay, and that way you will be end up forming so it will be replaced by a deuterium, the boron will be replaced, and it will be H. So that is the product you will be end up forming here. Now if you look into the options, different options, the first option seems matching with the product. here they have replaced the deuterium and H. I think the indicates, so the deuterium with n-butyl lithium, that means the boron will be with n-butyl lithium. That is not going to be the correct, because as I mentioned, because of the electron withdrawing capacity of the bromine, this carbon will be more electron deficient. Okay, so that cannot be the correct answer. They cannot be trans at all. Okay, the hydroboration always happening syn fashion. So the option A is the correct option here. Moving to the next problem here. So the major product A and B in the following reaction sequence are. So first thing, they are already mentioned that if you react with these, if you heat up, you will end up making a dimer. Okay, so let's think about what type of dimer it can form. Okay, now if you think about this, the reactivity, try to draw them. Okay, we can think about a inverse electron demand Diels-Alder reaction. Although in the inverse electron demand, we know that if your diene is going to be electron poor, then the corresponding dienophile has to be electron rich. But of course, if you heat up, you might able to get product here. So that can end up forming a Diels-Alder product. So let me just draw that first. Okay, so this will be the first option. So you can see from all the options, the option B and C looks the product. Now what is going to happen? They are going to treat with sodium borohydride with methanol. So if you treat with sodium borohydride with methanol, what is going to happen? We know that sodium borohydride methanol is going to reduce the corresponding carbonyl group. So that will give you this. Okay. Now if you treat with a tosic acid. Okay. So the tosic acid will be a strong acid. What is going to happen once you have this type of vinyl ether and you have given the strong acid, then this can able to take a H plus. So once you have a vinyl ether and you have a free alcohol here, this can allow you that can generate this oxonium species. Now this O is going to attack here, and that can able to form a cyclic compound. So you will be end up generating a cyclic product at the end. So you will have a methyl here, and you will have a methyl here as well, and the oxygen which is forming a bond here. Okay. So now you can see from all this option of B and C which you decided, the option B showing the correct option which you have, which you wrote here. Okay, that this oxygen is getting attacked here and forming this ring. So there will be a 6-member and a 5-member. Okay, that is the correct answer. So the B is the correct answer here. So let's move to the next compound. The major product B formed in the reaction sequence given below exhibit a carbonyl absorption band at 1770 centimeter inverse in the IR spectrum. The structure of A and B are. So the 1770 centimeter inverse in IR spectrum is indicating that it's a carbonyl compound. Okay, it's having a carbonyl compound. Of course, you can see in your starting material you will have a carbonyl compound. Okay, so let's first find out what is going to happen in the product. Okay, and from there we can able to find out more about it. So first thing is saying the 9-BBN and H2O2NOH. So if you see about this particular compound, I think we have covered some very similar example in the class, and I already show a tangent state of that. What I am trying to say that if you have a COOMe here in the above phase, then your boron will be try to approach to avoid the steric. It will be try to approach from the bottom phase. Okay, so that means the boron will be approaching from this phase, and it will be approaching like this. Okay, once it is approaching from the bottom phase, what is going to happen if you have used the 9 BBN? So that will end up you generating you this compound. Where the boron, the 9 BBN will be here, and you have a H here, having a double bond there, correct? So now you can think about that, in after that, what is going to happen? You treat with H2NaOH. So that can able to oxidize this to the corresponding alcohol. Okay, once you have this corresponding alcohol, you are treating with this, this reagent with methyl chloride and triethylamine. Okay. So you got the A compound. So let's see, which one going to be right among all these options. You can see this cannot be right, because once you have a hydroboration, this cannot come from the same phase. The boron cannot come the steric region, so that cannot be the correct option. This this is going to be the, because the boron and hydrogen adding in the same fashion, so this can be the correct option. Neither of these or the other one. And now you can see what will be the next product here. Okay. So we can clearly see that once we use a methyl chloride, okay, it is going to activate. So let me write down the other stereochemistry here. H. So once you have a OH and COOMe, I have already previously mentioned that this can able to react, okay, to form a lactone, because this is the once you have a once you have a alcohol and now if you try to think about the stereochemistry of this position, this is the, and there is double bond here, this is H and this is H here. So you can look into the product here, which is matching with the product which you got. Okay, so you can able to form this product here. The major product B formed in the following reaction sequences. What is going to be the product B here? Again, we can see first thing is a hydroboration treated with H3O plus, and then you are going for a reaction with the vinyl iodide, just now we have mentioned. So let's try to go for the first reaction. What is happening here? Again, the if you see the coming from this side to this side, again here there is, of course, although this is unsymmetrical, but due to the steric region here, the boron will be approaching from this side and the hydrogen is from this side. So you will be getting a syn addition here. Again, you can think about the the carbocation, which is benzylic, will be more stable. That is in the H is going to approach here, which you generally explain. Very similar thing in the case of styrene. That will allow you so there is a deuterium here, so it's not a hydrogen, so there is a BD, that is going to, so this is a catechol boron. So catechol boron going to add to the corresponding alkyne first, and then once you treat with H3O plus here, as I said, once you give acid, this is going to cleave the carbon boron bond to include the acidic proton, which is the H here. This is end of yeah, I think let me just go back. So it's going to first form this. So first I think the boron and hydrogen going to approach here, and then it is the hydrogen going to be approached. So of course there is not hydrogen, there is a deuterium here. We should be careful here because they are giving BD. So there is a deuterium going to approach here, and then you will be forming a bond here, a deuterium and a boron. Now you have a catechol boron here. You are treating this with vinyl iodide. So this is a Z vinyl iodide with palladium catalyst that is going to go for a Suzuki coupling. The Suzuki coupling which end up giving you product where these two deuterium will be. So now you can have this, there is a double bond here and a pH here, because again this this phenyl and this part will be in the same side, and these two hydrogen will be in the same side. So now we can just go through all the options we have here. So first option we can see here, the phenyl here, the deuterium is opposite side, and this geometry is cis. So that is the correct option we can see from here. The other options here you can see the deuteriums are not in the correct position, they are in the same carbon, and again here also they change the stereochemistry of this corresponding vinyl iodide, which after the cross coupling it is going to be the Z again. So that will the option A is the correct option. The major product formed in the following reaction is, so if you treat the L-proline first and then you are using this another H minus source, so you are using a reducing agent, the boron based reducing agent. So first thing what is going to happen if you have an isopropylaldehyde, you use L-proline. I think if you have gone through this asymmetric catalysis with proline based asymmetric aldol reaction, then here there is a acetone. So acetone is going to react with the corresponding proline, going to form the iminium. From there will be a equilibrium, it will be getting deprotonated to form corresponding enamine. Now this enamine is going to, of course you should make sure there is a acid always there, the proline, and then this is going to add to the corresponding aldehyde. Okay, so you have aldehyde here, and this is going to add to the phase of this aldehyde to get to the corresponding aldol product. So that way you will be generating this type of product, which will be finally hydrolyzed. A OH here, we can able to find out that, so it can form a plus here, and then once you hydrolyze it, it is going to form the corresponding the beta hydroxycarbon compound. Okay, but let's find out what will be the stereochemistry of that part. For that we have to kind of draw a tangent state to explain that. So let me just try to draw that. So it is going to have some sort of a 6-member tangent state. Okay, so here you have this the nitrogen, and here you will have H, and then we'll have a, okay, so the after nitrogen there will be double bond here, there is a methyl group in the down, and then there is a carbonyl group here which is coming from the corresponding isopropylaldehyde. Okay. So this is going to go through this type of 6-member tangent state to give you a aldol product, which you can see clearly, going to be product where the OH is actually in the above phase, having this, and then you have a CH2 and COCH3. So this will be a first product, and now once you treat with a Me4 NBHOAC whole 3I. So once you treat with, this is going to, this is actually known as a coordinating agent. So it is going to coordinate with the OH to form, and then it is going to coordinate with also this oxygen. So this can have a coordination here. Okay, now what is going to happen? It can transfer the hydride. It is coordinating here, so it is going to transfer from the, from the top phase here. Okay, so once you transfer from the top phase, it is going to generate the corresponding alcohol. Okay, you will end up forming this alcohol because the hydride comes from this top phase, the alcohol in the bottom phase. So if you look into all the options, this option A is the correct option here. Neither the B, they cannot be from the, so the hydride cannot be from the opposite phase, as this is, there is a chelation happening, that is allowing the hydride delivery in the same phase to form the alcohol in the, so the alcohol will be a, they have a different side of, like, if it is, if this is above, this will be below. So this cannot be the correct answer. Okay. Write down the major product in the following reaction. If you treat with this corresponding benzaldehyde and corresponding, the allyl boron compound. Okay, so here you have a protyl boron compound. What will be your product? Again, I think you have, if you have learned about allyl boron compounds, one of the important thing about them that, so here you have a pinnacle or bpin. It is known that they always coordinate with the carbonyl group, which is going to react here, and then through a 6-member tangent state, they are going to react with the, if you have a RH, that's how they are going to react here to form the product like this, where you have a allyl group, and you have a CH2 and then alcohol here. Sorry, you have a CH2 and then alcohol here. If it is simple allyl boron, then you will be end up forming a OH here with R. So you will be simply transferring a allyl group here. So let's talk about the next problem. Here we can see this is a problem of, you have a aldehyde and you have this, some sort of allyl boron species. Okay, that is going to react with the corresponding aldehyde to form the corresponding alcohol. If you remember, this allyl boron react this way, but the important thing is, one should try to think about the mechanism. There is a important coordination which is driving this reaction towards the product. So here the oxygen, the boron is coordinating with the oxygen here of the aldehyde. That is allowing you, so once this coordination happening, now this carbon is ready to, now this carbon is getting electrophilic, so that this allyl boration can be take place. Okay. So here we can think about what type of, then after the hydrolysis what type of product is going to be formed. We can see every cases we are seeing this alcohol, but we have to find out what will be the correct correct product here. For that we can try to draw the corresponding 6-member tangent state. Let me just draw it again. I think so. Let's draw a 6-member and then we will fill up. So what we are saying that if you have this is the one, if you have a boron here, and you have a double bond here, then you have to understand that you have a methyl which will be trans to it. This is the bond which is going to be formed, and then there is a there is a carbonyl going to be here which is going to coordinate with this. And now you don't want to keep this bigger group in the axial position, so you will be keeping this, if you have benzaldehyde, you will put the phenyl here and the H here. Okay, now what is going to happen, because of this coordination between these and this allyl boration is taking place, this is attacking here, and this is the oxygen boron bond is formation is happening. Going through some sort of a tangent state, if you try to draw the product from this, you can clearly see that we are getting a product like this, where you have a CH3 here or the methyl group, and here we can see the OH is up, or the first O bipene, which will be converting to the corresponding OH and a phenyl, okay, which after hydrolysis will be going to convert to the okay. So what we are getting trans product here with the CH3 and the OH. So let's look into the options. The first option seems correct, neither the second or the third or the fourth option. So in this particular part, I talk about several problems from the organoborane chemistry. Again, if you have forgot some of the things, you can go back to the notes. Again, thank you so much for coming to the class. I'm going to see you guys in the next class. Thank you.